Algebra 2 friends, here we are with section 9.5. We're going to be talking about classes of functions. So what are these classes of functions? Well, there's actually a whole lot of classes of functions, bunch of different types of functions. Sometimes we'll call them parent graphs, and they are listed here. So we have the constant function, which we can write generically as y is equal to some constant c. It's always going to produce a horizontal line. They have y is equal to a, but whatever. Okay, another function is the direct variation function. So we just talked about direct variation, and so basically this function is a linear equation that has its y-intercept. So you can think about y equals mx plus b, but the b value is 0, so it's just y equals mx, or y equals kx if you're thinking about direct variation. Always goes through the origin. Here we have y equals x, which is a play on this direct variation one. It's called the identity function. Basically, whatever y is, x is. So if y is 2, x is 2. Or I should have done it the other way. If x is 2, y is 2. If x is negative 1.5, then y is negative 1.5. You guys get it. It's this beautiful diagonal line. Y equals x. It's also in the linear function family. So I would kind of consider all of this one. Then we have the greatest integer function. We talked about this a while ago. Step function. Sometimes I call it the birthday function or whatever if you remember from previous conversations. So that's y is equal to the greatest integer of x. So x will be whatever x is, y is rounded to the integer that is equal, that is the integer that is the greatest integer that is less than it. So, all right, you guys can go back to that other video if you'd like to. Excuse me, or we can talk about it together. Sorry about that. At another time. Hopefully you remember that. This guy is the absolute value function. So when y would have been negative, this looks like y equals x, right? But y doesn't equal x. Y equals the absolute value of x. Therefore, when y was going to go down like this, because x was negative, it went boop, I'm positive. So whatever x is negative, y is positive. So we get this v function, or the absolute value function. Let me write it like this. Y is equal to the absolute value of x. Here we know what this is. Y is equal to x squared. We just talked about quadratic functions or quadratic equations. Here we have the square root function. You can imagine how we would get that. So if this is 1, so basically y is equal to the square root of x. So when x is 1, the square root of 1 is 1. When x is 1, 2, 3, 4, the square root of 4 is 2. When x is 9, we'd be all the way up to 3. You get how this is going. And of course, the reason why I didn't choose like numbers like 2, because the square root of 2 is like 1.41, blah, blah, blah. So that is not very easy to see. But you can see this guy and this guy as really representative points for that situation. All right. Now, over here, we have a rational function. So rational functions kind of have that hyperbolic vibe, right? So we have this situation where we have an asymptote, and sometimes we can have holes. So we know rational functions can look really interesting and different. If you play around with them, you could see some of them can even be all wild, like having like 2 asymptotes and a voomp and voomp, all kinds of wildness. So when you see this kind of asymptotic, vertical and horizontal asymptotes, you know you're probably dealing with a rational function, and we've seen that. And then finally an inverse function, which is also a rational function. So I'd kind of loop this all together, which is y is equal to 1 over x. Reminds you of the inverse variation, right? Because it was y is equal to 1 over kx. So it's kind of an inverse situation, and we've got this graph to go with it. So generally, if I am talking about functions like this, I will probably call these like parent graphs in a way, because what we'll do with these types of functions is we'll kind of riff on them. We'll start with these basic ones, and then we'll see them translated, dilated, stretched, flipped, all of this stuff. But if we know what the parent graph or the general function looks like, we have an easier time of graphing more difficult or translated representatives of the same thing. Let's take a look at this example. So identify a function given in the graph. So identify the type of graph that it represents. And so with this first one here, it looks almost identical to the square root function here. And so you can see like, oh, it's got that right shape. It looks like half of a parabola laying on its side, which kind of makes sense because you know y equals x squared is the parabolic function, whereas y equals the square root of x is this function kind of laying on its side. It looks like half of a parabola. And if you think a little bit about it, you'll see how they're related. But anyway, yes, this is a square root function here. And over here, this looks a lot like a linear equation and one that's passing through. It looks like a y equals x kind of situation. But this whole is peculiar. We don't get that. We don't get a whole like that when we're dealing with a direct variation or an identity function. We get holes like that when we have a rational function. So this is actually a rational function. Let's think about when we get a hole. So we might have like the function, okay, this is obviously y equals x. So we know that y equals x is the kind of a cousin function to what we're going to do here. But if I had y equals x with, what is this here? This is 3. Is this 3? Yeah, this is 3. So x minus 3 over x minus 3. Here we have definitely a rational function because here is like some, function up at the top and a function at the bottom, which they told us would be the case when I have a rational function. So p of x over q of x. And then I have this thing that cancels out to give me something that looks like y equals x, but it's not because y can't equal, oh, I see, it's not y equals x. That's why I was kind of tripping y'all. Okay, so this is 3, and I'm going to leave x minus 3 there, but clearly this is not y equals x because it would be like boom, 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 boom. So I don't know what this function is, but you guys get what I'm talking about, right? So this is like y is equal to like 5, 6x or something. It's like close to y equals x. Or it could just be a problem with the screen, the way that they drew this or the way that I copied it or something. But you guys get my point. So the overall take-home point is that this is actually a rational function. Yes, this is a rational function and not a direct variation function or the identity function. Okay, so Emily launched a toy rocket, here in example 2, from ground level. The height above the ground level, the height above the ground level h in feet after t seconds is given by the formula h of t is equal to negative 16t squared plus 80t. Which graph depicts the height of the rocket during its flight? Now, first of all, sorry for that hiccup. Please pause it and read it yourself. Make sure you understand, and then we should pick up. All right. So you see that this is the function. Now, one thing about identifying functions is not just identifying what they look like. Oh, this is a linear, this is quadratic, might be some kind of rational. It's being able to look at an equation and do the same thing. So hopefully you guys can see that this is definitely a quadratic equation. And quadratic equations will often result in a parabola. So it makes a natural sense that this is the answer. But even the situation seems best described by this shape. If you have a rocket and it goes up and it comes down, makes sense that it's going to have this kind of a pathway. So B is the answer. So in this example 3, we're going to be identifying and graphing these equations. So when I look at this guy, it's got the telltale absolute value symbol, so I know that this is an absolute value function. And this absolute value function looks just like the one that we saw with the v, except minus 1. And if you remember, when you have a minus 1, that's just a vertical translation down. So here's what I expect. Sometimes it's helpful to draw what I like to call the parent graph, or the function form that we saw in the chart above. And so we know that the y equals the absolute value of x looks something like this. But when I actually draw my graph, the one that we're asked to draw here, this one, I know that this minus 1 means to drop it down 1 point everywhere that I have a y value. So for every y value, though x being 0 meant y was 0 here, now x being 0 means that y is -1. Everything comes down 1. So now this is what my graph looks like. This one that I have in black here. This is the graph of y equals the absolute value of x minus 1. And you can, of course, plug in values to check that out. Let's turn our attention to this next one. Over here, this graph is clearly a direct variation with the k value being -2/3. So I think that this one is easier to just draw directly onto the graph instead of like starting off with the parent graph, because this is not a shift. It's actually kind of a reflection. That negative sign tells me that I'm reflecting it. So instead of a positive slope, it's going to have a negative slope. And instead of it being stretched, it's going to be kind of compressed because 2/3 is less than 1. I'm saying all that to say, let's just graph it like we're used to. So here's what I'm going to do. I'm going to start at 0 because all of these have a y-intercept of 0. And my rise, I could look at it as a +2, but my run has to be a -3. 1, 2, 3. Not that point, but this one. And these 2 points are enough for me to draw my graph. But I could also look at my rise as a -2, 1, 2. That means I go down. And my run as a +3, 1, 2, 3. So that's giving me also the -2/3 ratio. And then here is my graph. And that's really it for this lesson. So here's what I'd like you to do. I'd like you to make sure you feel confident about these couple of, these few 9,